You probably remember that position can be used to identify where an object is relative to a coordinate origin. For example, consider the two positions where x1 is equal to 2.5 meters and x2 is equal to negative 2.0 meters. Angular coordinates can be used in a similar manner to identify the angular position of an object relative to a reference line. The reference line is usually taken in the horizontal axis pointing to the right. Here, theta 1 is equal to 0.4 radians and theta 2 is equal to negative 1.2 radians. We note now that a radian is a unit of angle where 1 radian is equal to 57.3 degrees. Equivalently, 2 pi radians, which is a full circular revolution, is equal to 360 degrees. We have already seen that a change of position can be used to denote a translational displacement. For our example, the displacement delta x equals x2 minus x1. The resulting negative sign of the displacement denotes that the displacement is to the left, relative to the coordinate origin. A positive sign would have indicated a displacement directed to the right. Similarly, a change of angular position can be used to denote an angular displacement. Here, delta theta equals theta 2 minus theta 1. In angular coordinates, the sign denotes whether the angular displacement is clockwise or counterclockwise. For this example, the angular displacement is negative, meaning the direction is clockwise. Dividing the change of an object's displacement, delta x, by the time delta t over which the displacement occurs yields the average velocity of the object over that. The sign indicates which way the object is moving. In this case, it is negative, meaning the object is moving to the left, towards the negative direction. Similarly, dividing the change of an object's angular displacement, delta theta, by the time, delta t, over which the angular displacement occurs yields the average angular velocity of the object over that time interval. Angular velocity is usually denoted by the Greek symbol omega, and the sign indicates either clockwise or counterclockwise motion. The negative sign indicates clockwise motion. If we continue and divide the change of an object's velocity, delta v, by the time delta t, over which the velocity change occurs, it will give the average acceleration of the object over that time interval. Again, in a similar manner, dividing the change of an object's angular velocity delta omega by the time delta t over which the angular velocity change occurs yields the average angular acceleration of the object over that time interval. Angular acceleration is usually denoted by the Greek symbol alpha. Recall that in the limit as delta t goes to 0, the derivative dx over dt gives the instantaneous velocity. Likewise, in the limit as delta t goes to 0, the derivative dv over dt is the instantaneous acceleration. The same is true for angular motion such that, in the limit that as delta t goes to 0, the average angular velocity delta theta over delta t becomes a derivative equal to the instantaneous angular velocity omega. Likewise, in the limit as delta t goes to 0, the average angular acceleration becomes the instantaneous angular acceleration alpha. For every translational parameter you have met, there is a rotational counterpart. The primary difference is that in translational kinematics, things move in a line, while in rotational kinematics, things are spinning. In the translational world, the kinematics equations are the consequence of a constant acceleration. In the rotational world, the kinematics equations are the consequence of a constant angular acceleration. Thus, for every translational kinematics equation, there is a rotational counterpart. Let's do an example. Initially, a turntable is moving with an angular velocity of 1.2 radians per second. If its angular acceleration is negative 0.4 radians per second squared, and it accelerates for 6.0 seconds, what will be its final angular speed? Which equation would you use to solve this problem? That is correct. Now solve for the final angular speed and choose the correct value. That is correct. What is the significance of the negative sign in your answer? That is correct. The object has reversed its motion. Rotational values can be negative, but what does the negative sign really mean in the context of rotational motion? To understand this concept, let's go back to translational motion again. Assume you are given the velocity vector v equals -3 times the unit vector I. What does this mean? We can start by reordering the way it is written and put the negative sign with the unit vector. What does the 3 meters per second mean? That is correct. Speed is the magnitude of the velocity. What does the unit vector I mean? That is correct. What does the negative sign mean? That is correct. So this expression means an object is moving at 3 meters per second along a line in the negative x direction. So what does an angular velocity expression like omega equals -3 times the unit vector k mean? Let's start by reorganizing the equation like we did with translational motion. What does the 3 radians per second mean? That is correct. Angular speed is the magnitude of the angular velocity. What does the unit vector k mean? That is correct. Conceptually, a unit vector attached to a rotational quantity gives the direction of the axis about which the object is rotating. Thus, a spinning disk with angular frequency of 3 radians per second times negative unit vector k would correspond to the disk spinning in the xy plane and the axis of rotation along the negative z-axis as seen here. If the rotation axis is shifted by 90 degrees, you can see what happens. Thus, because the axis of rotation is always perpendicular to the plane in which the rotation occurs, and thus the direction of angular velocity vector is perpendicular to the plane of motion. Consider, for example, the rotation of a screw. Take up to be the positive z direction. Rotate a screw in the counterclockwise direction, as viewed from above, and the screw will move upward out of the block in the positive z direction. Rotate that same screw in the clockwise direction, and it will move downward into the block in the negative z direction. Going back to the spinning disk, we can use the sign associated with the unit vector to identify the direction of rotation. A negative sign corresponds to clockwise motion and positive to counterclockwise motion. So here, the rotation is clockwise. For the spinning disk shown here, which equation best describes the angular velocity? That is correct. The rotation axis is along the y direction and is rotating clockwise. Now consider the following example. A CD moving at -8 radians per second angularly accelerates for 5 seconds at a constant rate. If its final angular velocity is -18 radians per second, what is the angular acceleration? Which equation would you use to solve this problem? You don't know the final angle. Try again. That is correct. Now solve for the angular acceleration and choose the correct value. Check your calculations and try again. Check the sign and try again. Check your calculations and try again. That is correct. What is the significance of the negative sign in your answer? Compare the sign of the angular velocity and angular acceleration and try again. That is correct, since the angular velocity and angular acceleration have the same sign. Let's try another one. A CD moving at negative 8.0 radians per second angularly accelerates negative 18 radians per second squared through an angle of 12 radians. What is the final angular velocity? Which equation would you use to solve this problem? You don't know the time. Try again. That is correct. Now solve for the angular acceleration and choose the correct value. That is correct. To get the correct answer, you need to make sure you use a negative angular displacement based on the clockwise motion of the object. Now consider the following situation, where you are looking down on a rotating stick that has beads fixed at different locations along its length and assume the stick is moving with constant angular velocity. Let's freeze the motion at one point and consider what is happening to the beads near the center and at the end. Notice that the angle subtended by each bead is the same, relative to the fixed reference line. Now you probably recall that the arc length, S, is equal to the radius r times the angle theta. Keep in mind that r is the distance from the center of the circle, which is the pivot point, and theta should be measured in radians. Now, if it takes a time delta t for the spinning stick to go through this angle, then the velocity of a bead will be the arc length S divided by delta t. Thus, the velocity is equal to the distance r times the angular velocity. This is an important relationship between translational velocity and angular velocity that will be used again. It is interesting to notice that for each bead, although the angular velocity is constant, the distance r is different, and thus the beads are going at different linear speeds depending on where they are relative to the rotation axis. For this example, which bead has the largest translational velocity? That is correct.